we've looked at basically all the aspects, except the only one that we haven't really used VisiMix for is the reactive blending case. But we have a few problems that we're going to be using it to look at and see how well it does. But VisiMix actually has published cases where they've taken examples from textbooks and actually demonstrated how you can actually assimilate those. So now the last bullet here I mentioned. I mean, there are some data where the results from VisiMix deviate significantly. There's no question. Now, obviously, a tool like this would have limits, okay? Because it's based on some experimentation. Also, it's based on some theoretical analysis that they've done. But there are assumptions that are made. And so there are limits. Now, a tool like this should really a priori tell you what the limits are, but it doesn't. And so again, this is something that you have to be aware of. And so when you use a tool like this, you don't do one calculation. You always do multiple calculations. You do parametric studies to try and get a feel for, okay, is this thing changing in a reasonable manner for me? Okay. If it's not, then it's important that you note where you think there are some discrepancies. And I would say this, that the folks at VisiMix are actually very responsive. I mean, if you send them questions about it, they're quite responsive in addressing your challenges. If they find out that you're working outside of the limits or what is the fundamentals that are based on that you're validating some of the assumptions, they'll tell you. Okay? But the tool itself will not tell you that. So in closing, let me just talk about three cases, three applications. The first one here is a troubleshooting problem. The problem was poor mixing due to problem with powder drawdown. Okay, so you had a configuration in the plant, and they were having problem drawing down the powder. This is part of it was the fact that the particles were very light, and so it doesn't sink. But also part of it was the fact that it doesn't work very well. And so you need to find a way to draw it down, and in this case you want to create a sort of a little vortex in the center to draw it down. And so we looked at, and this is a 5,000 gallon process. You're adding about 7,400 pounds of powder. Not all, you're not dumping everything in at once, but adding over time. And so some of the constraints were that the impellers already operate at maximum rotational speed, okay, for the shaft design. And so you cannot increase the speed. And so what are some other things that you can look at? Okay? And also, air entrainment is undesired for this process. And so some of the things that we looked at was on the left is the previous setup where they had a pitch blade and a hydrofoil on the top and the location of it. And then on the right, we looked at a number of cases, actually, colleague over here, it was so that way. He looked at a number of cases and decided on the case that is on the right there. And this was implemented successfully in the plant. And this doesn't take a whole lot of time to be able to do because, as I said, because of the accessibility of the tool and so on, you can do these things very quickly. And in this case, we were relying on creating a vortex, but a vortex in such a way that it doesn't suck in a lot of the headspace gases and create a lot of bubbles in it. And so this was tested, and it worked very well for the plant. Here's a case where we're doing a scale up from a lab to commercial. We're going from 700 cc's to we're scale up of about 10,000. And here's a case where the work basically was done. You did the lab work with the 700 cc's, and you want to be able to convince somebody in the plant that proposal that you're making 10,000 times is going to work. Right? So what reactor to choose? They had a number of available idle vessels that they had to look at in the agitation systems because they want to reduce capital. This kind of thing happens all the time in facilities and plants where you want to reuse equipment that you already have. And so how to scale up the agitation. Lab tests show that the product quality was very sensitive to mixing or agitation. Too much or too little agitation will negatively affect the product. Now, we can't tell you what the product was and all the details, though, but at least we can share this part and what was the mixing time involved. And so again, we used VisiMix, and this was the case that was selected. And again, this was successfully implemented. Again, because of the accessibility of this tool, you can do this kind of assessment relatively easily. Okay. And case 3, this was a case where actually we're doing some computational fluid dynamics. But you realize that in most CFD calculations, you assume that the liquid surface is flat, which we know is not true. And the assumption that is made is that the flat surface does not affect the hydrodynamics. But if you carry out processes where you need a vortex to actually entrain liquid, entrain powders or something like that, then you cannot assume that it's a flat surface. Okay? Now, to model a surface like this in VisiMix, you have to use the volume of fluid, and it's not a simple calculation. And so if you can find a way to get the shape of the vortex and then patch it into your CFD, it simplifies things. This is exactly what we did. I showed you earlier that VisiMix is very capable of predicting the vortex in these state vessels and so on. So that was what was done. So VisiMix was used to estimate the vortex, and then that was patched into the CFD, and the CFD was carried out. And then the last case that I'm going to present here is a case where we were looking at solid suspension and distribution of heavy solids, very fast liquid solids. And the challenge here was, are we able to predict the distribution of solids, particularly near the surface, because they were going to be withdrawn material from the surface, and was it going to be representative of what's in the vessel? Okay, and so here was a tall tank with 3 pitch blade turbines that's running. And again, so we know all the properties, we know the geometry and so on, so you could simulate this very well in VisiMix. And also in this case, we actually did experiments with this particular setup that is here, and we compared the results with VisiMix. Now, you see here very clearly, typically measurement, when you do these kinds of measurements, what you find is for a shape like this is called this belly plot. People with, what do you call these, beer bellies. So it's a belly plot. Now, the result for VisiMix, it's okay, not very clear, but this green line, do you see that there? Yeah, you see that. Okay. So, I mean, VisiMix is not able to actually show this belly plot, particularly predicting the distribution of solids near the surface. VisiMix has a lot of difficulty in capturing that kind of information. But much below the top liquid surface, I mean, it does a pretty good job. Actually, I think it overestimates the uniformity of the solids in the liquid. So, basically what I've tried to show you here is that VisiMix is really an engineering productivity tool. It's simple, intuitive, and context relevant. It's very useful for characterizing and comparing well-defined mixing systems. And as far as we know, I mean, there is no other tool with a similar coverage and capability that is out there. There are a lot of tools out there, by the way. Lots and lots of tools, some based on spreadsheets, some based on some other models and so on. But in our search, we haven't found anything that comes very close. But it's important to stress that even with this capability, VisiMix it's a rating tool. It's not a design tool. Now you can use a rating tool if you do parametric studies to sort of cover the range of possibilities. And then the ultimate decision then is an engineering decision that you, the user of the tool, will have to make. And so you cannot come to this tool with zero knowledge about mixing processes. It's very important that it be emphasized. Now, it's limited. You cannot encode your own geometries and so on into the tool. The interface is simple, intuitive, and also context-relevant interface. And so you can interact with this. Any chemist, any chemical engineer, without knowing anything about mixing, can supply this information. And in a way, that is part of the rub, or if you will, the challenge of using a tool like this. You can give it to anybody, even a high school student. If you have the information, you can put that in, right? Now, the last bullet that I have here, well, first of all, I mean, you can use different units, SI units or US customary units. The calculations themselves don't take very long, so you can interact with this tool and get your calculations very, very quickly. But the rub here is that you saw the slides that I showed you. It doesn't say anything about what is the process result. That's not an input in this tool. And so you cannot come to this tool with zero knowledge about mixing and also about the process that you're dealing with. And that's a challenge, okay? Because you can come in here if you have a equipment and a process that you have all this information. You put it in and you hit a button and you get a result. Then the question is, what do you do with this information? Is it useful? Is it helpful? So that's a challenge with the tool. It's a rating tool, basically. You can define your process and hit a button and get a result. And it's important then to be able to understand. So you need to come to this with some knowledge about mixing and about your process. And then the third issue that we want to look at, okay, all right, if I get a result, is the result reliable? Can I trust this? Can I use this in my work? So the reliability aspects. And so the tack that we took was that let's compare it with some of our own data, and also let's look at some how it compares with some established correlations, things that also is published in the open literature. And let's take a look at not just the magnitude, but also some of the functional dependence. Let me just show you a few of the things that we looked at here.